All right, welcome. So in this video, I want to talk about an optimization technique called gradient descent in preparation for using it with artificial neural networks in the backpropagation algorithm. As mentioned, gradient descent is an optimization algorithm. The idea of it is to find a minimum. So gradient descent is focused on finding minimums, whereas there's a parallel or similar algorithm that we sometimes call hill climbing that's looking for maximums. They both sort of follow the same general principle, is we try and find the direction that the slope goes either down or up, whichever direction we're aiming at, and we follow that direction to hopefully find the minimum or maximum. As I mentioned, gradient descent is sort of the key optimization feature in the backpropagation algorithm that's used to minimize the error in artificial neural networks by modifying their weights. And we're going to take a look at that in our next video, but in this video, let's take a look at gradient descent. So we're going to start with a simple objective function. So this function here, I just picked a quadratic function. I kind of picked a somewhat random one. And it's just, we're trying to figure out where the minimum point is. So let's just take visually a look at this graph, or the graph of this function. Again, it's a parabola, it's a quadratic function, and we can see that the minimum point here occurs when x is 1, and we get a minimum of 0. And of course, we can just double check that by plugging it in. And so we're trying to find out what that, where that minimum is by, if we can chart the function like this, then we can just find the minimum usually analytically. But the purpose of a gradient descent is maybe we have a more sophisticated function than this one, and we can't maybe find the minimum analytically, and instead we're going to try and find it with this optimization technique. So the way gradient descent works is we're going to start by just guessing, if you will, or picking an arbitrary value to start our journey. So in this case, I decided to pick our initial value to be x0, and it's going to be equal to 2 in this case. So I take 2, I plug it into my function, f of 2, and I find out that's also 2, and so we have the point 2, 2. And if we're lucky, that might have been the minimum. We can see on our graph here that's not the case here. And so in any case, what we're going to do is we're going to look for the slope, as I mentioned, the gradient, we sometimes call this, or the derivative of the function to find the slope. So we're going to compute the derivative of f of x, which is going to give us 4x minus 4. And then we can plug in our current value of x naught, which is 2, which will give us the value of 4. So the slope at this point is 4. Now what we're going to do with that information is we're going to use that to determine which direction we want to move for our next guess. So we're trying to guess these points in a sequence, hopefully getting closer to the minimum. And so the slope tells us that if we increase our value, we will increase the slope. So our slope is positive. So that means as we go to the right, we will increase. So we want to go down. So that means we want to go to the left. So we're not going to increase our value. We're going to decrease our value. So you're going to see in our example here, we're going to compute a new x value to guess, and we're going to use it from the original x value. So we're going to take x0 and we're going to minus off the slope value that we've computed. Now it might be advantageous for us to subtract the whole value off. If we did, we would subtract off 4. 4 minus 2 would get us to minus 2, which is actually, we would have overshot the minimum by a great deal, and we probably don't want to do that. And so this is why we introduce a learning rate in the gradient descent algorithm, where we kind of want to take smaller steps in the direction of the slope. And so what we're going to do is we're going to assign some value here. We often call this alpha, although there's different names for it as well. We're going to call ours alpha, and I'm going to, for this example at least, I'm going to choose an alpha of 0.1. And when you are using gradient descent in one of your algorithms, selecting your learning rate is going to be one of the parameters you might need to balance to make sure that your algorithm, whatever it might be, backpropagation for example, is going to be successful at learning whatever it is that you're interested in. So in our case, I've selected my learning rate here at 0.11 because that's sort of indicative of sort of a commonly selective range, at least, of learning rates in sort of this 0.1. Maybe it's low as 0.01 up to maybe 0.1 is a sort of a common range. Depending on what you're learning, you might want to increase it above or below that. So I've just selected this as a representative, but also because it happens to give a good example, which was my goal here, was to have an example. And so in this case, by selecting 0.1, we take a relatively big step towards the minimum, but we aren't at risk of overshooting it, and that's usually a good way to pick your learning rate. Something that's going to approach you towards the minimum as quickly as possible without having a big risk of overshooting it when you get there. Okay, so in this particular case, I've computed my new x1, subtracting off that value gives us 1.6, and we can then repeat this step. So the next step of the algorithm is just to start over again with x1 instead of x0. So in this case, we'll start with 1.6, plug it in, find out which point that gives us on the slope, calculate the slope at this point. We went from a slope of 4, we moved down, so we're now at a slope of 2.4. And again, using the learning rate, we're going to use the same learning rate that's typical for a run of gradient descent. There are also more adaptive algorithms that might change the learning rate throughout the gradient descent. In this case, we're just going to keep it standard, so we'll just do another 0.1 step towards, and that ends up with a new point of 1.36. Now, keeping in mind, we already sort of analytically know that our minimum is at 1, and we can see that as we keep making steps from 2 to 1.6 to 1.36, we keep stepping in that direction. And so I'm just going to keep iterating here. So x2 is 1.36, x3 is going to be 1.216, again still making steps. The size of the steps getting smaller and smaller as our slope gets smaller and smaller as well. This is going to approach 0 because, of course, as we approach a minimum, assuming we have a nice continuous function like this, the slope at the minimum should be 0. So we're going to keep going, and I've just advanced us a handful of points to x7 now, and we can see that we're getting pretty close to that 1 point, but we might want to continue it a little bit further depending on what our goal is for the precision of the error that we're looking for. So at this point I decided the dots I'm drawing are all overlapping each other, so it's not going to be valuable for our example, so I sort of stopped here. And we can see that's pretty close. Now again, this is there can be different ways that you might want to stop your gradient descent algorithm. One way to do it is sort of like I did, maybe just pick a number like 8. We're going to do 8, and when we will stop at 8, that's very common. Another one is to use some kind of threshold on the error. So if you aren't changing very much, for instance, from one update to the next, that might be one that you would use. So you can have different kinds of ways to stop your algorithm. Of course, sometimes you don't always have a success with your first run, so you might run it again. That's another one. One interesting thing I just noticed numerically here, if you happen to see this pattern starting out, so the first number we had here was 1.6, then we had 3, 6, so 6 squared is 36, 6 cubed is 216. I didn't know that one, but I started looking them up. This is 6 to the power 4, 7,776 is 6 to the power 5, and so on. So there's actually an interesting pattern that emerged here as a result, and I'm really not really certain why that is, but it has something to do with the repeated subtractions that we're doing and the particular values we pick. Perhaps with a different learning rate, we would get a different kind of pattern showing up down below there. If you're interested in that kind of numerical stuff, go ahead and try this out with a different learning rate and see what you get. All right, so that first example was intended to help us just understand how gradient descent works. So we had a nice smooth curve and it was one-dimensional, so we could really understand how we were getting to the minimum in that example. It is very common that we apply gradient descent in higher dimensional spaces. In particular, I'm going to now do a two-dimensional example, but even that is considered a very small space. So for instance, in the smallest sort of backpropagation example that we're going to do in the next video, I think it's about a 6-dimensional space, which is still really small. For a common neural network, you might have one dimension for every weight that you might assign in that neural network. So if you have 1,000 weights, then you're going to have 1,000 dimensional space. Now, 1,000 dimensional space in my mind doesn't make a lot of sense. From a visual standpoint, I can understand what 2 dimensions are. I can understand what 3 dimensions are. I can even maybe stretch myself into thinking what 4 dimensions are. But 100 dimensions, 1,000 dimensions, that doesn't make sense to me. That's just a mathematical object now. So that's just a vector. So when it says here multi-dimensional vector space, what we mean is we just have a vector of variables, whatever they might be, weights in our neural network, and we're trying to optimize those. And we can still apply the gradient descent algorithm in these higher dimensions. So let's see how we can apply it in 2 dimensions so that we can then extrapolate and generalize that to higher dimensions. So for my 2-dimensional example, I want to start with, again, I just made up something and I picked this one. I sort of fiddled with it a little bit. I basically took a quadratic in X and a quadratic in Y, and I added them together. And then you'll also notice I chose to put a 1/2 out front. One reason I did that is just sort of foreshadow something that is commonly done when using gradient descent, which is in this particular case, we're going to need to compute the gradient, and to do that we needed to compute the derivative. And when we compute the derivative, there's going to be a 2 that's going to pop out either from the X or the Y, depending on which partial derivative we're going to compute. And when it pops out, it's going to cancel out with the 1/2, which just kind of makes our math look a little bit easier at the end. That's, we sometimes like that. So in this case, I just picked the 1/2. It's not as nice now, but it's going to cancel out at the end intentionally. So that's just one of the reasons that otherwise my constants are somewhat arbitrarily selected. All right, so I went ahead and plotted this using a web-based graphing calculator. And this is what we're basically looking at, the parabola, but there's 2 of them, one in the X dimension, one in the Y, and sort of generalized. And, sure enough, maybe this is what we might expect when we add 2 parabolas together. And we're looking for the minimum spot, and we can kind of see there's a minimum spot right here. Just by my design, I believe this is in position 2 minus 1. So the X and Y values that we need are X equals 2 and Y equals -1, and that will find that minimum spot. All right, so to begin, we need to, just like before, we need to start out an arbitrary spot. In our 1-dimensional case, we just picked an arbitrary X, but this is a 2-dimensional case, so we're going to pick an arbitrary point in that 2-dimensional space. And we could do the same thing with a n-dimensional space or a k-dimensional space. We can just pick an arbitrary point. It might just have n points. So if we had a 1,000-dimensional space, we just have 1,000 entries in our point. So in this particular case, we're in 2 dimensions. So we're going to have 2 entries, an X and a Y, we'll call them. And so I'll call the point x0, y0. And I'm just going to start at the origin, 0, 0. Why not? If you have no better indication of where to pick, why not pick somewhere, simple and well-defined? So one advantageous thing about starting at 0, 0 is we can probably compute what that's going to be quite easily, its actual value. Plugging in zeros, for instance. So what we're going to actually do is we're going to compute the gradient at this position. And gradient, remember, just means slope, or just means the derivative of this function. So we have our function here, f. It's now a multivariable function, x and y. But we're only going to compute the partial derivative relative to each of the variables one at a time to figure out the slope or the gradient relative to that variable. So we can think of that as the slope in the x direction and the slope in the y direction. And we're going to use those two to determine the actual slope and we're going to and the gradient or the direction that we want to move, and then we're going to move into that direction. So computing our derivatives, again, pretty straightforward, but maybe just a little bit trickier this time. Make sure you get everything correct, but keeping in mind here, remember the purpose of having the 1/2 was so that when we compute the derivative and we pull that 2 out front, it's actually going to cancel out. So we end up with just x minus 2 instead of, for instance, 2x minus 2 if we didn't have the 1/2 there. Now, in this particular example, that doesn't really do anything for us other than maybe make that variable a little bit prettier for us. But in other cases, this makes it just easier to compute, and we don't have to remember to, for instance, multiply by a factor of 2, which often in these cases, we're about to multiply by another weight, so that 2 can just be absorbed into that other weight in any case. So that's one reason why we might do this, just to simplify our math and simplify our code. All right, so we can do that again. Again, if you double check my math, if you like, we can compute the derivative with respect to y as well. Remember, when we're computing partial derivatives, that if we're computing it with respect to y, the other variable is treated as a constant, and so all those terms drop out. So we only are computing the derivative of the terms with y in it, and so that's why we get a much simplified version here. And so sure enough, we compute our two gradients, and then we can plug in our value of x0, and as I mentioned, when x0 was 0, 0, that makes it pretty easy to plug in. We just get minus 2 and plus 1. All right, now remember, minus 2 and plus 1 are going to be the gradients, and we want to move against the gradient if we're trying to minimize. We want to move down. So we're going to we're going to subtract those gradients off. And again, keeping in mind, we're going to apply a learning rate as we go as well. In this case, I'm going to select my alpha to be 0.3 for this example. Why? Well, I tried it out with 0.1. And when I did that, it was moving very slowly towards the minimum, so I wanted to speed it up. And this is a very common thing that you might do in, applying gradient descent, is you might notice, hey, my learning rate, or I've noticed my progress towards the minimum. Even if I don't know where the minimum is, you can still notice that your progress towards it is going slowly, in which case you might change your learning rate to hopefully speed it up. So that's what I did here. I changed it to 0.3 after using 0.1 in my previous example, and sure enough, this allowed me to, so let's do our first computation here. So we take our minus 2 plus 1, that's the vector we computed of the gradient, and we're going to multiply by our learning rate. So that gives us 0.6 and 0.3. But keep in mind, the minus of the minus, it cancels out, so we got our signs flipping over here. So we got 0.6 and minus 0.3, and sure enough, you find 0.6 minus 0.3. That's the first dot that we have here. And just repeating our algorithm, of course, we can keep doing this. We keep computing the slope, plugging in our new term, which is going to keep us jumping towards that minimum. I've indicated the minimum right here. It's at 2 minus 1, as I mentioned. And I only computed, I only wrote down 5 on the slide here, but I actually computed 10 jumps, including the original one. And we're still getting there, but we can see that we're starting to slow down a little bit as we approach. And so I can imagine even with another 10, we're not going to get, that much close. Well, we are going to get closer, of course, but we might still not be quite on that dot that we might want to stop. So in this case, what do we do? Just run it again. So 10 iterations is really small, of course, in an example. That's why we did that. But, if we feel like the number of iterations that we have is too long, then we can turn up that learning rate again. Okay, the risk, of course, being that if we turn it up too far, we're going to overshoot the minimum. What happens when we overshoot the minimum is we're going to bounce back because, assuming we've got a nice continuous function, then on the other side, the slope's going to go the other direction. So we get to the other side and we can think of it as just sort of rolling around at the bottom of that barrel. We're going to kind of oscillate back and forth. With a nice good learning rate, we're going to oscillate back and forth and probably come to a very rest. I want to say rest, but we'll probably switch back and forth between two sides very, very close to the bottom. But if our learning rate is too high, then we're going to jump back and forth keep overshooting that minimum by quite a lot. And that's one of the reasons why we don't want to have such a high learning rate. So we can definitely see there's a trade-off here in the learning rates between one, turn it all the way up so we can get really fast, get towards that minimum, but then also we want to turn it down to make sure we don't overshoot the minimum and we get close to the minimum. And of course, I mentioned at the beginning here, there are also sort of these adaptive algorithms that say, okay, well, what if we turn it up at first, maybe go fast to try and get towards some particular minimum, and then once we're maybe getting close to that minimum, we can slow it down a little bit and try and get, really find that one key minimum if that's what we're looking for. All right, so gradient descent is a great sort of tool for finding an optimum. Of course, hill climbing might find maximums. It's just the inverse version of this algorithm. Instead of doing the minusing, we do the plussing instead, try and go with the slope. This algorithm is actually really good at finding optimums. It can find minimums and maximums in all kinds of nice differentiable functions. Some of the drawbacks related to the gradient descent algorithm, of course, it's not the most it's a really good algorithm when it can be applied, but it cannot be applied in all instances. So one of the challenges that the gradient descent algorithm has, depending on your function, if you have a function like this that sort of has a local minimum, so the minimum here at 0, that's the local minimum, and then we have two other and these actually are equal to each other by the design of this function. I know that. So these would both count as global minima. So there would be two global minima in this case. And depending on where we start out our search, if we start out far on the left, we will hopefully come down to this one. If we start out far on the right, we'll hopefully come to this one. We can use some of our understanding of complex systems to think that what we have here are basins of attraction. This algorithm will be attracted to minimums, and depending on where you start it, where you put that initial point, it will be attracted to a specific minima, the basin of attraction of that particular minima. And if you put it in the wrong spot, we can call this the wrong spot because our goal is to find the global minimas, then we will get stuck in a local minima. So we will come down and we will find that minima, but it might not be the one that we're looking for. So we might in some cases, that might be close enough, and we might be like, yeah, okay, we're good. In other cases, we might be unsatisfied with that particular minima, and we might want a different one. So what kind of things can we do? Well, we can just rerun the algorithm. We can start it again. And so sometimes one way that we might do this, we might switch from an individual-based search where we just do this once to what we sometimes call a population-based search, where we spin up, several of these all at the same time, at which point we're starting to approach other kinds of algorithms like simulated annealing or evolutionary models. All right, another drawback of gradient descent is that if you have areas of your function that have no slope or zero slope, you end up not going anywhere. You don't know which direction to move. So I sort of made a small arrow here, but it ends up if you have a truly plateau, you won't get any movement without adjusting the algorithm in some way. On the other hand, if you have a very close to zero slope, so remember we said when we got close to that minima, our slope's going to get close to zero. And so as a result, we're going to make smaller and smaller steps. That was the goal when we had a minima. But when you have a plateau, it means we can get stuck on that. Or if we have really shallow parts of our graph, we're going to be stuck making really, really small steps. And so this is sometimes called a diminishing gradient when our gradients get too small. So we only make small steps and we're not near the minima where we want to be. So this can be bad for some functions. So what we're starting to talk about and what we're starting to see images of here are what we sometimes call the landscape or the functional landscape. And depending on what that landscape looks like, determines the success or failure of the gradient descent algorithm. And so another risk is that the opposite of a zero slope would be sort of a straight up and down infinite slope, or even a high slope. So diminishing gradients, we can also have exploding gradients, which is the idea of a really large gradient. If you have a really large gradient, what that ends up doing, even with smaller learning rates, is it might increase your step size a lot, because the idea is thinking that if we have this really steep one, we probably have to move a lot before it shallows out. But in this particular graph, we kind of have this deep little pit, and so if there's a lot sort of going on with this graph. If we got stuck on one of the plateaus, we might not move at all. If we happen to get lucky and get hit one of these walls that's telling us go down, so at least we have a slope telling us which direction to go down. The slope is so steep, we might make a big step size, and instead of jumping down to where we want to, we step all the way out and hit the plateau. So this is kind of a risky shape as well. Okay, so again, what happens when you have functions that don't have really good shapes? Well, one thing you do is you don't use gradient descent. You look to other optimization algorithms that might not have these same drawbacks. The other possibility you do in these cases is you try and reshape your function somehow, do something to it. So this function sort of has it all squished out here. What if we could stretch it somehow? What if we could really stretch this function in these two directions? If we know that that's something that might help our algorithm, then we could do that. And so that's a form of sort of pre-processing before we would perform the algorithm. All right, so I hope you enjoyed this video on gradient descent. In the next video, I'm going to talk about backpropagation. So thanks a lot for watching, and we'll see you in that next video.